Hello everyone, this is NK Pandey. In this video, I will be discussing some interview questions on mass transfer operation. I hope the question will be useful for aspiring and candidates. Let us start with some typical questions. What is called mass transfer operations? Mass transfer operations deals with the separation process such as distillation, solvent extraction, absorption, etc. And this separation process involves diffusion phenomena. These separation processes are characterized by the transfer of component from one phase to the another phase on molecular scale. Here, two phases must come in contact to each other in order to facilitate mass transfer. Mass transfer stops when equilibrium is attained. Hence, two phases are necessary. In majority of the cases, separation cost is major fraction of a chemical process, whether it is a raw material purification or product purification. Three states of matter, such as gas, liquid, and solid, permit six possibilities of phase contacts. These are gas, with few exceptions, uranium isotope separations and helium isotope separation. All gases are miscible with each other, hence no practical cases are realized. These are the combination of phase contact and related separation processes. In the case of solid, due to slow diffusion rate in solid, no practical cases exist. Suppose we have three cases. First one is water is evaporating from a pond or river. Second one, a solution is pumping through a pipe. And third one, a sponge absorbs solution containing solutes. Which one of these cases represent mass transfer process? Case A represents perfect mass transfer process. In this case, molecules of water vapor diffuses through the flowing stream of air. A concentration gradient of vapor molecules exist near water in air interface, which results in transfer of molecules from water vapor into the air stream. Whereas case B and C represents bulk transfer, hence cannot be called a mass transfer process. What is called molecular diffusion? Describe the governing laws of diffusion process. Diffusion is a movement of molecules from higher concentration to the low concentration region, which leads uniform concentration throughout the system. Suppose at time is equal to 0, small amount of dye is added in water. After some time, the concentration of dye becomes everywhere same, and this is the how concentration varies along the path of diffusion. Diffusion process is governed by two laws, Fick's first law and Fick's second law. As per Fick's first law, molar flux of a component A relative to an observer moving with the molar average velocity is proportional to the concentration gradient and is given by this, where J is the molar flux and dA is the diffusivity and dCA by dx is the concentration gradient. Molar flux is having unit mole per unit area per unit time. Area is measured here in the perpendicular direction of the flow. Fick's second law says change in concentration of diffusing molecules with the time at any distance x is given by del Ca by del T equal to dA del square Ca divided by del x square. This is in one dimension and this is also called diffusion equation. It finds application in material science, pharmaceutical industry, and food science. When this right hand side of this equation, that is when del square Ca dx square is equal to 0, then it becomes a steady state case, and this equation is converted into this Fick's first law, and when this right hand side of this equation is greater than 0, then system behavior is like this. And when this term is less than 0, so this is the system behavior. And when we solve this diffusion equation analytically or numerically, so we get a profile uh, of Ca as a function of x at various times, and which is represented here. Diffusivity is a strong function of temperature and is given by Arrhenius type of equation such as dA is equal to dA0 exponential EA by ERT. So here the dA0 is a pre-exponential factor, E is the activation energy, T is absolute temperature, R is the gas constant. I we take a logarithm, so we get a equation of a straight line. And when experimental data dA versus T is plotted, slope we will give the EA activation energy, and intercept will provide the pre-exponential factor value. And define molar average velocity and molar flux. And part B, what are different modes of mass transfer? Molar average velocity of a mixture is given by this relation, and the use of two types of fluxes are needed to describe the motion of constituent molecules. They are molar flux relative to a stationary observer, and second one is molar flux relative to an observer moving with a molar average velocity. First one is given by this relation, and second one, which is represented by J, is given by this relation. So this equation, by substitution, this equation becomes this one here. That average molar velocity is given by this one, and for binary mixture, this is given by this one. There are two modes of mass transfer: mass transfer by diffusion, which is given by Fick's first law, and second one is the mass transfer by convection, and is given by equation which is similar to the convection equation. And here volumetric mass transfer rate is equal to mass transfer coefficient and interfacial area and concentration difference. This is the general equation for diffusion and convection, and which is given by this here. And this equation is obtained from this here. Starting equation is this one, and someone has to do after some mathematical rearrangement, so we get this relation. What is the driving force for the mass transfer? Driving force for the mass transfer is chemical potential, not the concentration gradient. At equilibrium, uh, chemical potential of a component in gas or vapor phase is equal to the chemical potential of that component in liquid phase. Mass transfer stops when equilibrium is attained. Consider example here: a gas mixture containing ammonia, uh, concentration of 500 ppm, is in contact with water, which has a concentration of ammonia uh, equal to 800 ppm. So here concentration of ammonia in the gas mixture is less than uh, that of in water. So still the transfer of ammonia will take place from gas mixture to the water solution, because solubility of ammonia uh, in water is very high, and that's why ammonia, though it is in low concentration here, will be transferred to the water phase. That transfer will stop when equilibrium is achieved between these two phases. That means chemical potential of ammonia in gas phase is equal to the chemical potential of ammonia in water phase. So this is the concentration profile across the interface when a component A diffuses from uh, a gas phase to the liquid phase. What is mass transfer coefficient and its significance? Mass transfer coefficient K regulates rate at which equilibrium is approached. It controls the time required for the separation and also decides size and cost of the equipment. Mass transfer coefficient is influenced by physical property of the system and turbulence. A rate of mass transfer is a function of diffusion resistance, driving force, and interfacial area. Rate of mass transfer also is influenced by the physical property of the system. Diffusion resistance is represented here by the reciprocal of mass transfer coefficient. Uh, Different theories have been proposed to describe the mechanistic basis of mass transfer, which provided the relation for mass transfer coefficient for the liquid phase. Two important theories we will consider here. They are film theories and surface renewal theory. Surface renewal theory is not single theory, it is a class of theories. So we'll consider its two variation here. First one is Higgs penetration theory, and second one is Dunkworth surface renewal theory. Uh, First one will see film theory. As per film theory, there exists a diffusion layer inside by interface which offers resistance to mass transfer, and mass transfer in this diffusion layer is, is, give, is by diffusion process and is given by Fick's first law, and the mass transfer process across this diffusion layer is in steady state condition, and as per film theory, mass transfer coefficient is given by this relation, which indicates mass transfer coefficient is directly proportional to the diffusivity and inversely proportional to the film thickness. Uh, From experimental data, uh, it has been indicated that mass transfer coefficient is proportional to the diffusivity power of 0.5 to the 0.67, but whereas as per film theory, mass transfer coefficient is directly proportional to the diffusivity, though it is slightly away from experimental evidence, but it is widely used in design calculations due to its simplicity. Uh, His penetration theory uh, here will consider gas liquid cases here, and there is an interface, and uh, a liquid element here spends same length of time before it is being replaced by fresh eddies and to the bulk. Um, he says that all the liquid element spend same length of time at the interface, and during their stay it absorbs gas and uh, reaches equilibrium. Uh, Here, it is assumed that mass transfer process is unsteady state phenomena, and mass transfer coefficient is given by KL is equal to square root of diffusivity divided by pi t, and t is here exposure time, and uh, it is as per experimental finding it is close to the experimental observation, and here we notice that this uh, all constant exposure time here is a resemble of a plug flow condition where uh, uh, each element uh, or molecule in the reactor spend same length of time. So this behavior resemble to the plug flow condition, and after that, and Dunkworth says that this case, yeah, this phenomena may be applicable to for a particular case, and may not be true for all cases. And he suggested that uh, all the liquid element will not have same resident time at the interface, and it will have uh, a, edges of distribution of time. So that means all the liquid element will not spend same length of time at the interface. And he provided this relation for mass transfer coefficient here. Mass transfer coefficient is equal to square root of diffusivity into S. S is here surface renewal rate. Uh, Dunkquist theory is resembled to the CSTR behavior, where uh, uh, all the element of the fluid will not spend same time in the reactor. So this is resembling to plug flow cases, and this is a CSTR kind of behavior. Why mixing is necessary in all process equipment, such as in heat transfer, mass transfer, and reaction vessel. How to quantify intensity of mixing? Mixing is provided to increase turbulence, which in turn increases mass transfer coefficient as per this relation provided by Datus Volter. And we see here Sherwood number is a function of Reynolds number and Smith number, and Sherwood number is given by this relation. Reynolds number is this one, and Smith number. As turbulence increases, this mass transfer coefficient increases, and which results in increase in mass transfer rate. Moving also increases, mixing also increase in interfacial area. So in turn, both of these factors uh, increases mass transfer rate as per the relation here, which we have seen earlier. And this quantification of mixing is given by Piclet number, and Piclet number is a measure of intensity of mixing, and Piclet number is given by this relation. And when Piclet number is 0, it corresponds to complete back mixing, and when Piclet number is infinitive, it corresponds to plug flow condition. So in actual case, there is no uh, ideal vessel or ideal behavior. So in the real cases, behavior is in between CSTR and plug flow condition. That's all today. Thank you very much for your attention, and I will provide some more questions uh, in the next video. Thank you.